So this is our first of 3 lectures in Chapter 13, the last chapter we cover this semester. It's radiation exchange, so thermal radiation. That was the focus of the previous chapter. But now we're really focusing on exchange between surfaces. This is where I would say it gets very application-oriented. We're going to solve more problems. The previous chapter, Chapter 12, dealt a lot with the wavelength characteristics and the directional characteristics of thermal radiation. It laid the foundation for this chapter. Okay, so we're going to jump into what we call the view factor. The view factor is symbol F, and it'll be IJ. I meaning one surface, J meaning another surface. So maybe surface 1 and surface 2, or surface 1 and surface 5, or surface 2 and surface 3, whatever those I, J change. And then we're going to have an equation to calculate the view factor. This equation does not look pretty. It's 1 over area I, the double area integral, dAI dAj, of the cosine of theta I, cosine of theta j. Those are two angles from the perpendicular of surface I and the perpendicular of surface j of the line that goes between the point of interest on surface I to the point of interest on surface j. That's a little complicated, but that's what that is. And it's divided by pi r squared, and r is the distance between the point of interest on surface I and the point of interest on surface j. So this is a double area integral. This is one of those reasons why this class is so hard. You go to solid mechanics, you go to fluid mechanics, you go to any other class that you've already had, and you say, is there a double area integral? Oh, not just an area integral, an integral area twice, dAI, dAj. This is unique. This is challenging. All right. This is not a pretty integral, but that's our calculation. We're going to derive that equation briefly. We'll use it very briefly, but then we switch over and we say, well, what is this meaning of this view factor? It's the fraction of the photons that leave surface I that hit surface j. We don't say what they do after they hit surface j. We just say they impinge on it or they hit it. So it's the fraction that leave I and hit j. Once you have that physical insight, then you can say, look, there's a summation rule. The summation rule says that the sum of all the view factors from I to j over all surfaces j that make an enclosure have to equal to 1. 100% of the photons have to go somewhere. And it's bookkeeping to make sure we find out where they all go. 20% may go here, 30% may go here, but we have to be able to account for all of them. They have to sum up to 100%. And then the last one, rule or reciprocity rule, is that if I could send photons and they can hit you, guess what your photons that come off of you can do? They can come back and hit me. Photons travel in a straight line. So basically the equation goes like AI Fi to j times, or is equal to Aj times Fj to I. We're going to derive that one too. But the concepts of the summation rule, the concept of the reciprocity rule is simple. The concept of what the view factor is simple. Mathematically, not so obvious. Okay, we're going to then focus on how to deal with black body radiation exchange. So we'll come up with this geometrical resistance. We'll have something that drives the flow, represented like a temperature, but it's not a temperature by itself, but it's like a temperature. It's what drives the flow, and the temperatures will be at the nodes, or what drives the radiative exchange will be at the nodes, and then we'll have some resistance. And this geometrical resistance is 1 over AF. 1 over AF. Kind of funny. You mean the same view factor? Yeah. And then you say, well, is it 1 over AI f I to j, or is it 1 over aj f j to I? Well, from reciprocity, they're the same, so a lot of times we just drop the subscripts because they get awkward, and we just say 1 over AF. 1 over area times the view factor. That is a geometrical resistance. What drives the flow? Well, if we're doing black body radiative exchange, it's the EBI and the EBJ. Okay, so it's not just temperature, but it's related to temperature, because what is EBI? The black body emissive flux or power, which was given by sigma Ti to the 4th, and over here sigma Tj to the 4th. You could see that a lot of engineers worked hard to try and make these calculations doable. A lot of helpful bookkeeping strategies like resistor networks that helps us keep track of things and not lose terms or drop terms. So it's the sigma T to the 4th that drives the radiative exchange. And then we'll be able to deal with enclosures using the summation rule, have a network, and all of our nodes are these EB nodes. What are they given by? Sigma T to the 4th. Well, we're not going to be able to get this far today. Let's try and get through the first 2 sections. We have 3 lectures in this chapter. So, the big one is the view factor. The view factor is given by this mathematical equation. All right, so you look at it and you say it's a double area integral. Very unique. I integrate over area 1 as well as at the same time integrating over area 2. Okay. I have the cosine of theta I and the cosine of theta j. Let's say this is my surface out here, j. And you have to have a side to it, so it's pointed this way. Surfaces have sides. One side may be, conduction on the back side. It's the face of it that's pointing out into some enclosure. And then over here may be another surface I. And this is the side, the face that has radiative exchange. What we have to do is we have to do an area integral from every point along, and I've only shown it in 2D. It really is a 3D problem. And every point along surface J, and we sort of connect them. And then what we do, let's say grab this one and connect it with, let me just kind of grab this point and connect it with that point, like that. Okay, what you'll have is you'll have for this point connected to that point, you'll have a distance r, and then you square it. That you're dividing by the distance r. And this angle right here is theta I. Let me get rid of this line. It's a little confusing. And here, the theta j is nearly 0. But there's an angle theta j as well. Okay? So that's what these 2 angles are, theta I and theta j. They're the angle with respect to the normal of each of those surfaces to the line that's connecting those 2 points of interest. All right. So this is how we calculate that double area integral, and you have this 1 over AI. Don't forget the 1 over AI out in front. What does it mean? Well, it's going to be a fraction. The view factor from I to j will always be between 0 and 1. It can be 0, it can be 1. Okay? And it represents the fraction of the photons, or the fraction of the radiation, that leave the diffuse surface I. There's embedded in it that we're dealing now only with diffuse emitters, diffuse reflectors, diffuse surfaces. There's no directional preference to them. If I say a diffuse surface, maybe the image of this comes into your mind, where a lot of the photons are going off straight up, and fewer are going at shallow angles off the surface. Okay, this was a concept in the previous chapter, and it doesn't say what they do other than they impinge or are intercepted by, or they hit surface J. They travel in a straight line and then they go there. You could see that this is set up if you do numerical calculations for something like Monte Carlo ray tracing. Do a lot of that. You could do it, calculate these view factors with Monte Carlo ray tracing, if you like computers. Let's solve a problem. Let's try and do that integral. I think it's just, forget the derivation, let's just try and do it. Okay, so we have surface A1. Okay, here is surface A1, here is surface A2. Surface A1 is pointed downward. It's hard to show, but it's pointed downward, facing downward, okay? And surface A2 is facing upward, okay? So A1 is a 2x1 rectangle. It's parallel to the XY plane, but it's at a location Z equal to 2. So X, Y, Z, so it's sitting there. Hopefully that makes sense to you. Parallel to the XY plane, but it's at an elevation Z is equal to 2. It's facing in the negative Z direction, facing downward. Okay. Then area 2 is a 2x3. So you go out 1, 2, 3, and then you go out 1, 2, and there it is. That's our rectangle. It's facing upward. And it is in the XY plane at elevation Z equal to 0. Okay, so this seems like an easy problem. Can't get hardly any easier. Calculate that view factor from 1 to 2. Well, what was our equation? Our equation is 1 over the area 1, the double area integral, cosine theta 1, cosine theta 2 divided by pi r squared, dA1, dA2. Well, let's break this down easiest. Anybody help me with what is A1? Its length here is 1, and its length here is 2, so it's 2. Now, we didn't put meters in there, so let's just say it's 2, whatever, inches squared, or meters squared, or centimeters squared, whatever the lengths are. Okay, so that's what the area 1 is. That was the easiest term to do. Okay, what you have to do is you have to say, I have to integrate over every point on surface 1 and connecting it to every point on surface 2. It is a nasty integral. You never had an integral this hard in all of your calculus classes, period. Why not? I don't know. They didn't prepare you for this class. Heat transfer's tough. It's like math on steroids. Add double, triple, isn't it? Have you ever done an integral like this? So if I was going to integrate over A1, I would bust it into maybe an integral of dx1 dy1. And then I would integrate over A2. I would integrate over, and now I'm going to kind of put it over here, dx2 dy2. Now you got real confusing because you have two subscripts, on the x, x1 and x2, but it's integrating over the x variables with respect to the first and second area. Let's kind of flush this out because we're going to have 1, 2, 3, 4. All right? And so if you can get the lower and upper integral with respect to x correct, that'll be a big accomplishment. So how about you do that? How about everybody on this sheet of paper, I'm going to pause, I'm going to walk around. I want you to put in what are these lower and upper integrals that have to match. So this pair matches x1, this pair matches the y1, this pair matches the x2, this pair matches the y2. If we can't get the limits correct, forget about the integrand, which is more challenging than limits. So get those down. I'm going to walk around. So, Pablo, you have 0 to 2, then you have 0 to 1, then 0 to 2, then 0 to 3. Perfect. Great. Now, that was hard. Now, we're either going to work with pi. Oh, that's easy. Leave pi in there. the r squared or the cos. I think the r squared is a little easier. Okay, so what you have to do is you have to say, kind of letting x1, y1, x2, and y2 be just variables. They can range between the limits, right? For like 0 to 2, 0 to 3, 0 to 1. So it's like just sort of pick a random location at this point. What is that point described by? That point's described by its location x2 that's moving out this way. X1, y1, right? And then just grab a point down on the second surface. Let's move it over here. And it's at location x2, y2. Okay, connect them. That distance is r. But I don't want simply the distance r. I want the distance r squared. So give me an equation for what r squared is in terms of those four variables, x1, x2, y1, y2. Not that hard if you think about it. Just go ahead and give me what is, because I need this r squared right here. Right? So can you do that? I'll walk around, pause and walk around. All right, so to get this r squared, you think of a parallel pipette. Parallelepiped. It's a little box, three-dimensional box, right? That goes, I'm going to try and draw it like in 3D, right? I'm not very good at this. And so this goes from this point up to that corner. And the distance squared is this distance squared plus that distance squared plus that distance squared. It's like Pythagorean's theorem on steroids. Three-dimensional Pythagorean's theorem, parallelepiped. Diagonal. So the r squared is the, let's say this is my delta x, change in the x. This is the change in the y, and this is the change in the z. So it would be delta x squared plus delta y squared plus delta z squared. Professor, why don't we take the square root? If we took the square root, we'd get r, but we really need r squared, so let's not take the square root. And then somebody says, well, I know what x squared, delta x squared, it's x1 minus x2 quantity squared. Should that be x2 minus x1 or x1 minus x2, or does it make a difference? It doesn't make a difference in this case because it's squaring. It's just the difference in the x. Likewise, it's the y1 minus y2 squared. And then what about the change in the z? That's the only thing that's a constant. It's at a height difference of 2. So it's 2 squared. It'll be 4. That's what r squared is. So now that we have that one, we are almost ready. So here is r squared. I'm not going to try and write it in there. It's to figure out this cosine of theta 1. And then figure out the cosine of theta 2. Just like you remember this little parallelepiped or Pythagorean's theorem in 3D, for the cosine of theta 1 and cosine of theta 2, you remember from statics especially, I know we cover it in statics, how to get the dot product in 3D. And the formula for the dot product in 3D, let's say vector A dotted with vector B, is equal to the magnitude of vector A, magnitude of vector B, the cosine in 3D of the angle between them. So if I'm looking to get the cosine of an angle, a lot of times it's like, hey, can I get two vectors, A and B, dot product them, divide by the magnitude of A, divide by the magnitude of B? That'll give me the cosine of the angle. I need to do that for 1, and then I need to do it for 2. Maybe down here it's a little easier to do it for 2. Draw up a perpendicular vector. That perpendicular vector is perpendicular to the surface A2. Isn't it coming up? And so guess what that vector is? It's only in the z. It's only in the z. And you can let that vector go from here all the way up to there. It's like going the whole parallelepiped thing, right? And so you can make that vector a unit vector, or you can make that vector length 2. Your choice, you just have to remember what you did with it. Okay, let's do this one. Let's call this vector B. Let's call this one vector A. And because I know what that vector A is, it's that whole parallelepiped thing, right? So what I'm going to do is I'm going to have now, this is the angle theta, and this is my theta 2 equation. I'm looking for that. Okay, so trying to finish it down here. What would be B? Would be any change in the I? No. Any change in the J? No. Change in the Z? Yeah. We're going up a positive 2Z. That's a K, sorry. Put the K there. 2K. Okay. Now let's get vector A. Well, I'm going to have a change. Now I have to be a little more careful. I'm starting at 2 and ending at 1. So would it be x1 minus x2 in the I? And then it'll be y1 minus y2 in the J. And what will it be in the K? Plus 2 in the K. Remember, A starts down here at 2 and goes up to 1. Okay. Now that I have those, you have to be able to get the magnitude of B. Let's do that one. What's the magnitude of B? And then the magnitude of A. What's the magnitude? I'm going to pause. I'm going to walk around. Give me the magnitude of B and the magnitude of A. All right, so a lot of us got that B is 2 and A is delta x squared plus delta y squared plus 2 squared square root. That's the length. And then you look at it and said, well, that length is R, isn't it? Take those two vectors and give me the dot product. Professor, I need my equation sheet. No, you don't. All right, so the dot product of the vector A with vector B, it just turns into 2 squared, which is 4. All right, now we're ready to do it. Cosine of theta 2 is equal to A dot B, 4 divided by the magnitude of A, which is R, and the magnitude of B, which is 2. It just turns out to 2 over R. It's really nice, isn't it? Now, R does vary on where is x1 and x2, where is y1 and y2. R is not a constant. It's a function. We wrote it over here. This is R squared. Okay. Guess what? I ran out of room, but guess what? I'm going to scroll down just a little bit. Guess what the cosine of theta 1 is if you do the same math? It's going to be 2 over R. That's what it's going to work out to be. 2 over R. One of the reasons is the perpendicular for theta 1 is aligned with the perpendicular of theta 2. I mean, the one is pointing up and one is pointing down, and you're doing the cosine of the angle between the same connecting rod, the same R. So that really helps. So let's see if we can summarize what this equation now boils down to. To calculate the view factor from 1 to 2, I need the 1 over the area 1. We got that. What was my area 1 again? It's 2. Then we had the integral. We had the cosine of theta 1, which is 2 over R, times the cosine of theta 2, 2 over R, divided by pi R squared. Then we had this dA1, dA2. Okay, dA1, dA2. This boils down to the you already worked out all these 4 integrals with dx1, dy1, dx2, dy2, right? And now we can see that it's 2 over pi r to the 4th, isn't it? And so now we can even expand it a little bit more. View factor 1 to 2 is equal to integral 2 over pi. Now the r is x1 minus x2 squared plus y1 minus y2 squared plus, I'm going to put 4 instead of 2 squared. And then all of that is raised to a power, and I want you to give me that power. Is it 1? Is it 2? Is it 4? Is it something else? And then dx1, dy1, dx2, dy2. Let me pause, walk around, and I want you to give me that power. Very good. A lot of us got it correct. It is squared. That term squared is r to the 4th. So how would you solve this integral if you had to? Well, yeah, with a computer. There you go. Now, what do you think about using the aid of Wolfram Alpha, internet available? I had to write integral, integrate 4 times. I had to use the right parenthesis, etc. Yeah, I could have gotten rid of that, whatever, put 2 over pi. But then didn't we get the right r to the 4th? Now, it's hard to put x1, x2, so it's like integrate x and then to b, a, which is the next one, and then y to b, the second y, call it b. So, but it works on the y minus b. B again would be the second y variable, and a would be the second x variable, just to help clean it up. And this did a few times. It coughed up and said, you've exceeded your allocation of free time. So I had to figure out how to change it up a little bit. I wasn't looking for an analytic solution anyway. But this is a 0.24. Close enough. Okay, now there's more digits if you want them. But it's 24%. Let's go back and look. Basically, okay, 24% of the photons that leave surface 1 go down and hit surface 2. Where do the other 76% go? They go off and don't hit surface 2. They miss surface 2. But 24% do. Okay, 23.7%. The derivation for this view factor. It's not trivial. It builds on what we did last time. So think of surface 1 and surface 2 as sketched right up here. Surface 1, surface 2. They both have outward directed normals. If I take a point and I connect it there, it could have been a point here to a point there, whatever, then you'll have the definition of what r is, the separation distance, and you'll have the definition of theta 1, theta 2. In this sketch, theta 1 looks similar to theta 2 in magnitude, but they are not. They can be very different. Okay. All right. So now if you ask the question, what is the radiative exchange between these two black surfaces? They're black, meaning perfect emitter, and they're going to emit at the diffuse surface. Then you say, okay, what is emission from 1 that's going to go and hit on 2? If it hit on 2, it's absorbed at 2. So this is kind of some funny notation, but I'm not trying to say what's the net exchange. It's just what goes from 1 to 2. So it's the intensity of the black body emission from 1. Then you have to multiply it by the little normal, because that's how the definition of intensity is. So you're like looking back from 2, looking back. So that dA1 normal is dA1 times the cosine of theta 1. That's how we're starting to get these cosines in that equation. And then times the solid angle in steradians, that 1 goes to 2. So then that depends on the magnitude of A2, and then it's also the cosine, because you want to get it to be this area orientation, so you need the cosine of theta 2, and then it's divided by r squared. That's our equation for this term, the little solid angle. And then this term right here for black body emitter is constant. So it can come outside the integral. And now you see that you have an area integral, an area integral. You have a cosine theta 1, cosine theta 2. You have a 1 over r squared. And so all that works out. Then you remember what is the relationship between the intensity and the black body emissive flux. Well, it brings in this pi because of the hemisphere. I know it's not 2 pi, but it was associated with the integration over all the solid angles. And so if you want to replace and use the EB1 right here, it's EB1 over pi. So bring the pi inside the integral and leave it there. And then this EB1 is sigma T1 to the 4th, the black body emissive power. And this is that fraction that goes from I to J. That's the definition of the view factor. We could play with it a little more. I'll do that on the next slide. And basically, 1 to everywhere is just the area 1 times the black body emissive flux. And then you do this ratio to get the fraction. This is the fraction from 1 to 2. The EBs cancel, and you're left with this nice equation for the view factor. And so you can think of it as the fraction of the photons that leave 1 and go somewhere, but that go and hit 2. There it is. So it's a double area integral. It's very, very, very hard to do. We just did one, but believe me, you very rarely do it. Very, very, very rarely do it. Okay, a couple questions. I'd left my base so they're not clicker questions, but can the view factor be negative? Looking at this equation, it may be hard to tell, but thinking of the definition of what the view factor is, can it be negative? No, it cannot. How about can it equal 0? Yeah, it can. If I had a surface oriented that way and a surface oriented that way, how are the photons from this one going to go and land on that one? No, they can't. They're shadowing. There's like, no. Okay. Can the view factor equal 1? Sure. Let's say I have a surface that's 1 is outward pointed like outer surface of a pipe, and then I have another inner surface of a pipe. Well, all the photons from the inner surface are going to hit the outer surface, from 1 to 2. And so, yeah, there's a case where it is 100%. All right. The integrand in the view factor is blah, blah, blah. The cosine of theta j is a function of the location on area 1 or area I. Unfortunately, it is. It's like this is all balled up. It's like this is dxi, dyi, dxj, dyj. Okay, well, all 4 of those affect what is the cosine of theta I as well as the cosine of theta j as well as what r is. Okay. In the integrand, can the integrand be negative? Can this be negative? Cosine of an angle, pi r squared. Well, you have to think. What do you think is the range of theta I? Can it go between 0 and pi, or is theta I restricted between 0 and pi over 2? If it can go larger than pi over 2 and you start to go toward pi, well, you're going to get a negative of the cosine of that angle. But if it can only go between 0 and pi over 2, it will go from 1 to 0, but never go negative. So what about this theta I or theta j? Can they be greater than pi over 2? They make no sense to be greater than pi over 2. Think about it. You got that surface, there's your normal, and it would be like this. No, you're coming to the backside. That would be the r, and this would be, no. Theta I is always between 0 and pi over 2. All right. Summation rule. Okay, so if you have a view factor I to j, if I sum for any I over all the j's in an enclosure, you have to have an enclosure that's equal to 1. So let's say I have a surface, let's call this one surface 1. And then I have surface 2, then I have surface 3, then I have surface 4. I've shown in 2D an enclosure with 4 surfaces. So the view factor 1 to 2, well, I also have to consider 1 to 1, which is kind of weird, plus view factor 1 to 2, plus view factor 1 to 3, plus the view factor 1 to 4. See, 1, the photons, because it's slightly, what do you call that, concave? Some of the photons, let's say from this side of 1, could skim out and hit surface 1. Not a lot, but you could get, 1 to 1 could be something. Then you could get 1 to 2, 1 to 3, 1 to 4. They all have to add up to 100%. If I look at this problem as shown, look at the shape of surface 3. The view factor 3 to 3, what do you think that is? How many photons leave surface 3 and hit surface 3? Hit another part of surface 3? 0. It's just not possible. How do you determine that mathematically? I just do it by inspection. This is where it throws students off. Once you get a good grasp what the view factor is, sometimes you could just do it by inspection. Let's do that pipe. 2 surfaces. This is the outer surface of an inner pipe, and this is the inner surface of an outer pipe. And so we're analyzing radiative exchange in the annulus. Again, this is surface 1, and that's surface 2. What is the view factor 1 to 1? Can they leave? No, they can't leave surface 1 and somehow go in a straight line and hit surface 1. And then if you said I only have a 2-surface enclosure, what is the view factor from 1 to 2? 1. It has to, by summation rule, they're going to hit 2. All right. Now the hard part, view factor 2 back to 1 and the view factor 2 to 2. This is not 0 and this is not 100%. Some of the photons from 2 can go and hit surface 2, another location on surface 2. Some of them will hit surface 1. Okay, to answer these questions, we're going to need another rule. The first rule in view factor calculations, summation rule. The second is reciprocity rule. The photons from this surface can go and impinge on that surface. What can the photons of this surface do? Go back and impinge on that one. You could see this mathematically in our view factor calculations. What was our, let's say this is surface 1 and this is surface 2 right over here, okay? Let's do the view factor 1 to 2. Isn't it the area 1, the double area integral of the cosine theta 1 cosine theta 2 divided by pi r squared dA1 dA2? Okay, take that equation, modify it by taking both sides and multiplying by A1. Likewise, write an equation where you have the view factor 2 back to 1. 1 over area 2 this time. Let me write that cleaner. 1 over area 2, double area integral, cosine theta 2 cosine theta 1 divided by pi r squared dA2 dA1. Does the area, the order of the integration matter? Or whether no, those can be swapped. And so I then multiply both sides of the equation by A2. And guess what? This integral is equal to that integral. Hence, the product A1 times view factor 1 to 2 is equal to A2 view factor 2 back to 1. It's kind of like the fraction that leave 1 and hit 2. Well, I know how big 1 is. Now I know the total number flowing over there. Likewise here, the fraction 2 back to 1, but multiplied by A2. So this gives me the net equivalent exchange. This is the reciprocity rule. Sometimes written AI Fi to j is equal to AJ Fj to I. Now you can go back to this other problem that we're just looking at, can't you? You can use the reciprocity rule to figure out these other two. Let's do it. Let's say this 2 to 1 right here. So we're going to say the area 1 times the view factor 1 to 2 is equal to area 2 view factor 2 back to 1. Okay, this is my surface 1 right here. Its area is pi d1, some length in the third dimension. The view factor 1 to 2 was unity. Area 2, pi d2, length in the third dimension. And the unknown, what I'm trying to solve for, f2 back to 1. The pi's cancel, the length cancels, and the view factor 2 back to 1 is really just the ratio of diameter 1 to diameter 2. If diameter 1 is really close to diameter 2, it's nearly 100%. If diameter 1 is really, really small, well, there's the solution for what that view factor 2 back to 1 is. And then once I know that, guess what I do over here? I get 1 minus d1 over d2. Where did that equation come from? Summation. You'll get very good at saying, oh, this is by inspection. You make inspection, then summation, then reciprocity, then summation. Kind of jumping back and forth to figure out all the view factors needed. You can solve some really difficult problems. I'm not going to spend the time on it. This one's derived in the book. What's the view factor from surface 1 to 2, where actually they are joined at a point. And they have two lines of equal length, W, and they're separated by an angle, alpha. And you find the view factor 1 to 2 is 1 minus the sine of alpha over 2. And it uses symmetry, reciprocity, summation rule. You know, that's the way you solve these problems. You have to solve a few of these. Have a problem. You want to go back and stay with the cylinder inside of a cylinder. That's a two-surface exchange. Let's say this is surface 1 and this is surface 2. If surface 1 has T1, temperature 1, then it has EB1, which is sigma T1 to the 4th. It's emissive flux. All right. If surface 2 is characterized by temperature 2, then you have EB2, which is sigma T2 to the 4th. If T1 is greater than T2, guess what? There's going to be an exchange. There's going to be a net radiative exchange going between the two, right? So what you do is you say, well, if I have, I bust it out and I say, what is Q net from, I'm going to think of 1 is hot. Q net is going to be 1 to 2. Okay, well, it'll be the difference between Q that leave 1 and hits 2 minus the Q that leaves 2 and hits 1. I mean, I know they're long subscripts, but the concept is here. So I have to say, how much is leaving 1? What's the rate at which, what are the watts, the rate at which radiative energy is leaving 1? Well, won't it be the product of A1 times EB1? Yeah, isn't that it? If I know how big the area is, and then I know it's watts per meter squared, units of this are watts per meter squared, then I know how many watts are leaving 1. Then I multiply by something to get that hits or impinges on 2. Well, that's the fraction. That's our view factor. And then we say, okay, focus now on surface 2. What leaves surface 2? A2, EB2. Okay, what's the fraction that goes and hits 1? 2 back to 1. Okay, let's do a little playing with this equation. So it'll be the A1 F1 to 2 minus A2 F2 to 1. Whoops, sorry about that. Now this is EB1 minus A2 F2 to 1 EB2. Okay. What is the relationship between these terms. Is A1 F1 to 2 equal to A2 F2 to 1? By what? Summation or reciprocity? Reciprocity, they're equal. So I can actually combine these. So the Q1 to 2, the net, this is a net transfer, radiative exchange, will be A1 F1 to 2 times EB1 minus EB2. And then you look at it and you say, the difference, this is the difference that drives the flow. What flow? The radiative exchange. And then you think, well, this is my analogy with the resistors and circuits. I is equal to delta E over R. What law was that? Ohm's law? I know I write a little different, but it's the flow, I, the current. Delta E is the difference in electromotive force or voltage, and you divide by some resistance. And guess what you do? You do name calling, and so we have this resistance is equal to 1 over AF, A1 F1 to 2. This is some geometrical radiative resistance. Geometrical radiative resistance. It implies or is used for diffuse surfaces. Black surfaces are definitely diffuse. They're perfect emitters. They emit in that diffuse profile. So no angular preference. And this is a nice way of bookkeeping and keeping track of radiative exchange and enclosures. So this is a big equation that we come up with. Consider two large parallel plates. If they're two large parallel plates, they have the same area, and the view factor from surface 1 to surface 2, the view factor from 1 to 2 is 100%, and the view factor 2 back to 1 is 100%. They're flat plates, they're infinitely long, blah, blah, blah. Okay, on the top plate, okay, I drew them side to side, whatever. Okay, change orientation quick. Here's surface 1, here's surface 2. And the top plate has a temperature T1 of 1200 Kelvin, and the bottom plate T2 of 400 Kelvin. Calculate the net radiative exchange per unit area between the plates. So we want to get 116 kilowatts per meter squared. That's the answer. Well, I'd set up a little radiative network. I'd put a node here and a node there, and I'd put a little resistance in between. What is that node? EB1, EB2. This is a geometrical resistance, 1 over AF. And so the flow from the hot to the cold, Q, the Q is equal to EB1 minus EB2 divided by 1 over AF. This is going to be A times F times EB1 minus EB2, which is sigma T1 to the fourth minus T2 to the fourth. And so Q divided by area, that's my flux, is equal to this view factor, sigma T1 to the fourth minus T2 to the fourth. All right, so you just put in view factor is 1, Stefan Boltzmann, 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth. And then we're going to put in our T1 of 1200 Kelvin to the fourth minus our T2 400 Kelvin to the fourth. I like to put my Kelvin to the fourth outside till I explicitly cancel my units. And then I calculate that this is the answer. Makes sense? Maybe that was a little easy, but it's setting us up for a little harder problem. So what's the slightly harder problem? You put a radiation shield in the problem. What do? Well, you have two plates. One plate's 1200 Kelvin, one plate's 400 Kelvin. And then you put a thin, opaque sheet. What's that word opaque mean? Can't be transmitted through there, right? So let's go ahead and put it in there. And the sheet is black, blah, blah, blah. So what we have is we have some radiant exchange between the top plate and the sheet, and then between the bottom of the sheet and the bottom plate, right? And so this is a 1 over AF. This is a 1 over AF. The view factors in all these cases are 1. Real easy. Okay. And so you have the 2 resistors in series. Guess what you do with those resistors? You add them. They're in series. So the equivalent resistance is 2 times 1 over AF. All right. So when we put it into our equation, we have Q is equal to, you have sigma T1 to the 4th minus T2 to the 4th. And then we have 1 over that resistance, 2. Then we have the 1 over AF, or 1/2 area view factor sigma T1 to the 4th minus T2 to the 4th. And so this Q divided by area is 1/2 of our previous answer. It's this factor of 1/2. So by inserting just a black sheet, you've reduced the radiative exchange by 50%. It went from 116 kilowatts per meter squared. You divide that in half. What is that? 58 something kilowatts. So the answer is 58 kilowatts per meter squared. All right, what do we got? 10 minutes left, right? Let me take a look, see if I've got anything else. Let's move into radiative exchange in 3 surfaces next time. But this section, this whole chapter is really important. We've covered a lot of very important ground. Hopefully it makes sense to you. Please start solving problems in the homework. Thank you for your attention. I'll see you next time.